Hello people and welcome back to another video. In this video, we'll be starting off from where we left last. If you remember in the last video, I have given you guys a question based on the concept of normal distribution that we have seen in the previous session using R programming. I hope you all have at least tried to solve this question on your own once. If you guys have tried it, in this session, I'll be starting off by solving this question and telling you guys the answer to this question. You guys can verify it from at your end whether you have followed the same approach or not. So we'll begin by solving this question. So the question reads, assume that the literature on the topic suggests that the distribution of days of hospital stay are normally distributed with a mean of 5 and standard deviation of 3. Use R to determine the probabilities below based on the normal distribution. So you have been given the mean value as 5 and you have been given standard deviation as 3. What percentage of patients in the hospital are in the hospital for less than 10 days? So 10 days is going to be somewhere here. So essentially in the first part of the question, you need to calculate this shaded area. Okay, so let's do it. So we need to calculate the percentage of patients which are in the hospital for less than 10 days. So in the previous session, we went over the concept of pnorm, qnorm, and dnorm, which are important commands in R, which will help us in solving different types of questions on normal distribution. Now, this particular question asks us to find the probability given the point, which means we will be using pnorm. I'll go back and I'll just write here pnorm. So less than 10 days. We have been given mean as 5 and standard deviation is 3. So this comes out to be 0.9522096, which means approximately 95% of the patients are in the hospital for less than 10 days. Now let me remove this portion. The next part, what percentage of patients are in the hospital between 3 and 10 days? So 10 is again somewhere over here. 3 is somewhere over here. This is 3. This is right here is 10. So we are concerned with this area, which is between 3 and 10. We have already seen a similar example like that. So you know what you have to do. You have to calculate here. So this gives you the percentage of patients who stayed for less than 3 days, and this has to be subtracted from the percentage of patients. This comes out to be around 69.97%. So this is the answer to this particular question. So I hope you guys don't have any further doubts in this particular topic. We'll move forward to two very important concepts. First one of them being sampling. Now, why is sampling extremely important? Because sampling is a concept that is key to statistics, and this concept is carried forward in, I would say, the rest of everything that we're going to be studying in the fundamentals of machine learning. And why is that? It's because, as I mentioned in the very introductory lecture of this particular series of modules, that there is a fundamental difference between population and sample. Population is the complete data set which has an exorbitantly large amount of rows. Sample is a small section of that particular population. So what we do in statistics is that we know the information of the sample, or we are aware of the information with respect to the sample. And what we try to do is that we try to extrapolate and make conclusions about the population parameters from the sample parameters, which is why sample and sampling, both of them are important and key concepts to understand. Now, the fundamental definition of sampling, as I mentioned, is to select a part of the population. So, for example, if out of 10 million records, I'm choosing 2,000 random records, then that 2,000 records set is referred to as a sample, which is taken from a population of 12 million rows of data. Now, while we are sampling, we must take care of a few things. As I mentioned, that sampling is a key process when it comes to the larger goal in this process, which is to make conclusion about the population. And because this sample will be extremely pertinent in making those conclusions, we need to make sure that the samples in and of themselves have no biases within them. Which is why the important thing while we're choosing a sample is that each element which is present in the population should have an equally likely probability to be part of that sample. What I mean by that is, if I have a population of about 12 million records and I have to choose a sample of around 2000, then each element in my population or each record in my population should have an equal probability, which is in this case 1 by 12 mil. This should be the probability of each element of getting selected, and the selection of the sample has to be done at random so that we can make the best estimates for our population. There are different parameters which we will look at in future modules when we'll solve more and more problems when we're estimating population parameters from sample parameters, or I should rather say population parameters from sample statistics, because any any mathematical notation associated with a population is referred to as parameter, and the conjugate of that is a statistic, which is more referred to a sample, or it's more adjunct to a sample. So all in all, when you will study hypothesis testing in the later modules, we'll understand in a little more detail the nitty-gritties and the intricacies in population estimation from sample. But for the time being, I would like to move on to another key concept, which is central limit theorem. Now, essentially, what central limit theorem tells us is that when you have a sample from a population, and you do the process of sampling multiple times. So let's just say that I have a population of size 10 mil, and I'm choosing a sample of size 15. Now, what central limit theorem says is that if you repeat this process of sampling, and the process of sampling is to select a random sample from a population. If this process is repeated multiple times, then the distribution of the mean of all of these samples will follow normal distribution. So there are two pertinent conclusions that we can draw from a large sample size or repeating the process of sampling multiple times, that the distribution of the sample means will be closer to the normal distribution, and there will be a smaller variance of the sample mean. So if you do this process, let's just say the process of sampling 15 sam 15 observations from a population of 12 million, and let's just say I do it 10,000 times. So what you will observe is that the resulting distribution of sample means will be normal, and the variance of this normally distributed curve will be extremely small. To go further and elucidate a little more, central limit theorem also talks about the size of the sample. So in the first case, we discussed the process of sampling. Now, what sampling is to repeat the process of taking a sample from a population multiple times. But we haven't spoken at depth about the size of the sample itself, which is, if I have a population of, again, let's just say 10 mil, then what does n, my sample size, what is it about the sample size n that central limit theorem tells us? Now, central limit theorem tells us that it does not matter what kind of distribution your initial population has. Your initial population can be normally distributed, can be exponentially distributed, it can be a normal distribution skewed to one side, it can be a uniform distribution, it can be anything. However, when you choose a sample of size greater than or equal to 30, this is the magic number in statistics, your sample distribution of means will follow a normal distribution irrespective. Let me repeat my point. It does not matter what kind of a distribution your initial population has. If you choose a sample of size 30 from that population, or 30 or more, then your distribution of sample will be a normal distribution. To move on to more mathematical details, if I have a population with population mean as mu and standard deviation as sigma, if you choose a sample of size greater than or equal to 30, which means it follows a normal distribution, your mean of sample is going to be same as the population mean, and your standard deviation of the sample is going to be population standard deviation divided by square root of n, where n is the size of the samples. So this is all that I have for you guys when it comes to central limit theorem. I hope you guys have enjoyed the video. I'll see all of you all in the next video. Thank you so much for watching.